In mathematics, a linear approximation is a method used for estimating the value of a function f near a point x equals to a, using the formula that is presented in this video. This formula is known as the linearization of f at x equals to a, and is identical to the equation of the tangent line to f at x equals to a.
In this video, we will see the graph that is an example of how drawing a tangent to the original function at a given point is used to approximate non-linear function.
Through this video, we can notice that linear approximation has several applications. For instance, it is used in different sciences such as physics and economics.
Approximation is used to compute most of the stuff on a computer, however rarely linear approximation. For example, every trigonometric function is implemented using approximation. Linear approximation becomes important if you don't have an explicit formula for the function. For example, it is important in solving nonlinear equations or differential equations, where the function is the unknown variable.
And we will use economic application of linear approximation, and in this case, a graph of demand. Real-life demand function is not linear. And to make models and theorems easier to understand, we can use linear approximation, and in this case, we will draw a tangent to the original function at a given point.
Taylor series is an expansion of the idea of the linear approximation. In fact, it helps to find a better match to the original function, and secondly, to find a polynomial to match the function. Most functions are smooth over ranges we're interested in, and polynomials are also smooth. So for every smooth function, we should be able to write down a polynomial that approximates it pretty well.
The Taylor formula is fundamental. It gives us an equation for the polynomial expansion for every smooth function f. However, the actual formula is not that simple. There are several conditions that should be satisfied.
First of all, the original function should be infinitely differentiable. Secondly, the polynomial should be equal to the origin function at the given point.
Then the nth derivative of the polynomial should be equal to the nth derivative of the original function.
The idea behind the Taylor expansion is that we can rewrite every smooth function as an infinite sum of polynomial terms.
So here we have the formula of the Taylor series, and we also have these two restrictions on the Taylor series approximation. The first one is that the polynomial at the given point a should always equal the value of the function at point a, and the second one is that the nth derivative of the polynomial should also equal the nth derivative of the original function at a given point a. So let's try to construct this formula. Firstly, we have a polynomial with one term, and obviously it should be the function at point a, because that's the only way. If we put a instead of x, we have the polynomial equals the function at a. So this try makes sure that the first criterion is satisfied. Let's add the first derivative of the polynomial of the function and to make sure that these restrictions are satisfied. So if we add the first derivative of the function times x minus a. So the reason why we have this term is that whenever we put a instead of x, it becomes 0 and this is cancelled. So we are left with the value of the function at a. So that this criterion is satisfied, and when we differentiate the polynomial, this is deleted because it's a constant, and what we are left with is the first derivative of the function, because the derivative of this term is 1. So this makes sure that the second restriction is also satisfied. So let's move on and add the second derivative of the original function. Here we have the same polynomial plus second derivative of the function times x minus a in the power of 2 divided by 2. So the reason why we have the a2 in the denominator is that whenever we differentiate this term and apply differentiation rules, this 2 comes and we have the power of this term cancelling the 2. So what we are left with is the first derivative of the function plus the second derivative times this. And if we try to differentiate it for the second time, this is cancelled because it's a number, and what we are left with is the second derivative of the function at point A. So again, the second restriction is satisfied. So let's go on for the last time and add the third derivative of the function. So we have the same polynomial plus third derivative times x minus a in the power of 3 and 2 divided by 2 times 3. So the reason why we have this is the same as here, because if we apply the differentiation rules and we differentiate it once, this 3 is cancelled, and if we differentiate it for the second time, this 2 is cancelled. So basically we differentiate it once, we have this, we differentiate it for the second time, we have this, and if we differentiate it for the last time, we see that the third derivative of the polynomial is equal to the third derivative of the function at point A, which makes sure that this criterion is satisfied. So if we continue this way, we can see a sequence and try to have the formula of the general element of this polynomial, which in this case is the nth derivative of the function at point A times x minus a at the power of n divided by n factorial. And as we can see, this is the same as that's how we arrive to the formula of the Taylor series.
That's all, folks.